Today we will learn about the most famous experiment in all the history of physics called Michelson-Morley experiment. Most of the wave that humans have been encountered in nature wave is wave in the water, sound wave or wave traveling along a road. As we know, wave is a disturbance in some medium. Water wave are disturbance in water. Meanwhile, sound wave are disturbance in particle of a water or some solid. But what about light? When light display or has wave-like properties, a very natural assumption was light must also be a disturbance traveling through some types of a medium, even if that medium was not easy to detect. In the 19th century, physicists thought that there is some types of medium that light is disturbance traveling through. They called it as the luminiferous ether. In that time, physicists all around proving that the ether existed and figuring out what our relative velocity was regarding to the ether. But in 19th century, there is no tools that can measuring the speed of light precisely. However, the most famous experiment in all the history of physics, called Michelson-Morley experiment, was designed to detect the motions of the Earth through the luminiferous ether. In 1887, Albert Michelson and Edward Morley performed an experiment to prove the existence of ether. Albert Michelson built an extremely precise device called the interferometer. This device is used to detect the ether wind. Shortly, we will see how it is work. There is a light source, and the light source is emitted to the beam at the center. Half of the light is reflected up to the mirror 2 and mirror 1, and when it hits the mirror, the light is reflected back. The two lines are recombined at the beam and reflected to the other side of the beam, where they make interference fringe. Let's see how it's work when there is an ether. The motions of the Earth in the ether at speed v generate an ether wind with velocity v. Light beam that travel time t2 parallel to the Earth motions, interference with a light beam that travel time t1 perpendicular to the motions. According to the ether wind theory, the speed of light should be c plus v as the beam approaches mirror 2 and c minus v after reflection. In the right-angled triangle, where c is the hypotenuse and v is one of the sides of the triangle, so the speed of the beam to the mirror 1 and back is square root c square minus v square. We can express the speed of light using the Galilean time interval. L0 basically is the distance between the beam and the mirror. L0 for the first one is the distance of the speed of light from the beam to the mirror, and the second one is the distance of the light traveling through from the mirror to the beam. This time difference between the two instants at which the reflected beam arrives at the viewing detector gives rise to a path difference between the beams, producing an interference pattern when they combine at the positions of the detector. A shift in the interference pattern should be detected when the interferometer is rotated through 90 degrees in a horizontal plane, so that the two beams exchange roles. This rotation results in a time difference twice that given by this equation. Therefore, the path difference that corresponds to this time difference is this equation. Because a change in path length of one wavelength corresponds to a shift of one fringe, the corresponding fringe shift is equal to the path difference divided by the wavelength of the light. In the experiment by Michelson and Morley, each light reflected by mirrors many times to give an effective path length L of approximately 11 meters. Using this value, taking V to be equal to the 3 to the power of 4 meter per second, which is the speed of the Earth around the Sun, and using 500 nanometer for the wavelength of the light, we expect a fringe shift of 0.44. The instrument used by Michelson and Morley could detect shift as small as 0.01 fringe, but it detects no shift whatsoever in the fringe pattern. The experiment been repeated many times since by different scientists under wide variety of conditions, and no fringe shift has ever been detected. Therefore, it was concluded that the motions of the Earth with respect to the postulate ether cannot be detected. At the end, the purpose of the Michelson-Morley experiment to establish the existence of the ether is forgotten. The ether existence remained unsolved, and more precise Michelson-Morley experiments serve as further proof to the non-existence of the ether. In 1905, Einstein solved the problem with his special theory of relativity. Before, we noted that the impossibility of measuring the speed of the ether with respect to the Earth and the failure of the Galilean velocity transformation equation in the case of light. He based his special theory of relativity on two postulates. The first one is the principle of relativity. The laws of physics must be the same in all initial reference frames. And the second one is the constancy of the speed of light. The speed of light in vacuum has the same value, c equal to 3 to the power of 8 meter per second in all initial frames, regardless of the velocity of the observer or the velocity of the source emitting the light. Nonetheless, the null result of the experiment can readily understood within the framework of Einstein theory. According to his principle of relativity, the premises of the Michelson-Morley experiment were incorrect. In the process of trying to explain the expected result, we stated that when light traveled against the ether wind, its speed was c minus v, in accordance with the Galilean velocity transformation equation. However, one always measures the value to be c. Likewise, the light makes the return trip after reflections from the mirror at speed c, not at speed c plus v. Therefore, the motions of the Earth does not influence the interference pattern observed in the Michelson-Morley experiment, and a null result should be expected. If we accept Einstein's theory of relativity, we must conclude that relative motion is unimportant when measuring the speed of light. At the same time, we must alter our common sense notions of space and time and be prepared for some surprising consequences. First is the simultaneity and the relativity of time. Second is time dilation. Third is the twin paradox. And for the fourth is length contraction. Fifth is the space-time. And last but not the least, the relativistic Doppler effect. Light is now understood to be an electromagnetic wave which requires no medium for its propagation. As a result, the idea of an ether in which this wave travels becomes unnecessary.